Hi everyone, in this video I'd like to spend a bit of time to discuss the role of the second derivative, f dash dash of x, and in particular I'd like to show you how it's connected to a function's concavity. Now, in the upper right hand corner of the screen here, you can see a brief description or summary of what a function's concavity actually tells us. Put simply, it tells us how the function's derivative or gradient changes. In other words, the concavity of a function tells us whether its derivative is increasing, so getting bigger and bigger, or decreasing, so getting smaller and smaller. And to illustrate that, I've split the screen into two. We're going to look at different types of increasing functions as well as different types of decreasing functions. And in each of those cases, we're going to be talking about the second derivative, and therefore the concavity. So let's get started. Say I have part of a function's curve that looks something like this, increasing like so. So that's some portion of a curve y equals to f of x. Now what I want us to focus on for a second is how the gradient of this curve is changing as we go from left to right. And one way of picturing that is to draw steps going from left to right of the curve. Here's what I mean. I could start with a small step like this. I then make a second step with the same width, so like that, and another, and another, and another, and another. And although this is just a step, what I want you to realize here is the amount I move along horizontally for each step is the same. What we notice here is that the amount by which we have to go up for each step keeps on increasing. And in fact, we could think of each of these steps as showing us the rise over the run. We notice here that as we move along this curve, the rise over the run, in other words, the height of each of these steps, keeps on increasing. And so I could actually go ahead and write rise increases. That's increases. And remembering that gradient is often defined as rise over run, the fact that the rise of each step is increasing tells us that the gradient is increasing and therefore that the first derivative, f dash of x, is increasing. So I'll just write f dash of x increases. In other words, this curve is getting steeper and steeper as we go from left to right. And since f dash of x is increasing, the second derivative, f dash dash of x, is positive. And I'll go ahead and box that. And when the second derivative is positive, we say that the function is concave up. And we sometimes say concave upwards. But I'll just go ahead and write concave up. And it's worth pointing out that a function doesn't have to be an increasing function for it to be concave up. Indeed, if I look at a decreasing function for a second, something looking like this. There we go. And let's say once more this is a portion of some function y equals to f of x. And just as before, I'm interested in seeing how the gradient, and therefore the derivative, of this function changes as I go from left to right. So let's see if I draw my little steps again. So I would draw one here, another one here, another one here, another one there, and so on. We can see that as we go from left to right, we initially make a large step downwards, then another step downwards, and another, and another, and another, and so on and so forth. But notice here that as we go from left to right along the curve, the amount by which we have to step downwards is decreasing. And the word downwards here is very important. What we're dealing with here is a negative rise. So I'll just write negative rise. And this is important because although it looks as though the steps are getting smaller and smaller and smaller, the way to think of this is that the negative rise is actually getting bigger and bigger and bigger. So in the same way that negative 2 is bigger than negative 3, which is bigger than negative 4, and so on, the rise of the steps as we go from left to right here is in fact increasing. And so just as before, I could go ahead and say that the rise increases, and therefore, the first derivative, f dash of x, is actually increasing. So I'll just write f dash of x increases. And so once more, the second derivative, f dash dash of x, is positive. And I'll box that as well. And I'll write concave up again. Concave up. Done. So these two curves show us what a concave up function looks like. In each of these two cases, the first derivative, f dash of x, is increasing as we go from left to right, and the second derivative is positive. And in fact, if I were to combine these two graphs, And I'll just make a little space there to do that. I'll just erase a few dots. There we go. Meaning if I drew a curve looking something like this, we can see here that this curve is concave up. Indeed, the left-hand side of this curve here would correspond to what we saw here, and the right-hand side would correspond to what we saw here. And we notice that this curve goes through a minimum point. So I'll just write minimum right there, minimum. And as we'll be seeing when we learn about the second derivative test, on either side of a minimum point, the second derivative has to be positive. And that will often be one of the ways used to show that a point is indeed a minimum point. That being said, let's look at some concave down functions. We'll start with increasing concave down functions, and a typical example of that could look something like this. There we go. We can see here that as we go from left to right, the function is clearly increasing, but if I draw some steps here, just as I did before, so I'd have one step there, another step there, another one there, and so on and so forth. We quickly see here that the rise of each of these steps is getting smaller and smaller and smaller. Indeed, if I draw over those in blue, we have the first rise here, the next, the next, the next, the next, and so on and so forth. These blue line segments are getting smaller and smaller and smaller as we go from left to right. What that tells us here is that the rise is decreasing. So I'll just write rise decreases. And just as before, since we think of the gradient as the rise over the run, since the rise is decreasing, the gradient is decreasing, and therefore the first derivative f dash of x decreases. Decreases. And since the first derivative is decreasing, the second derivative f dash dash of x must be negative. And I'll go ahead and box that result. When a function's second derivative is negative, it's known as a concave down curve, or a concave downwards. So I'll just go ahead and write concave down. Concave down. There we go. And looking back at the portion of the curve we have here, which was part of some function y equals to f of x, what's noteworthy is that for an increasing concave down function, as we go from left to right, the curve is getting less and less steep. In other words, it's kind of flattening out here. And that's one way of easily recognizing when the second derivative is negative. Lastly, we look at a decreasing concave down function. We'd have something looking a bit like this. And again, this is a portion of a function, so that's y equals to f of x. And as we go from left to right, we can clearly see that this function is decreasing. But if I draw my steps, so the first one would be here, then I have another one there, another one there, another one there, and so on and so forth, we quickly see that as we go from left to right, the amount by which we have to go downwards is definitely getting bigger and bigger and bigger. And remember that for a decreasing function, this rise is negative. And I'm tempted to say that the rise is getting more and more negative. And so, although it looks like these steps are getting bigger and bigger, we need to think of this in the same way that we think of -4 being smaller than -3, which is smaller than -2, and so on. In other words, the rise here is in fact decreasing. So I write rise decreases. And since the rise is decreasing, the first derivative, f dash of x, is decreasing. So I'll say f dash of x decreases. And since the first derivative is decreasing, the second derivative, f dash dash of x, is negative. And I'll go ahead and box that, and once more we can say that the function is concave down. And just as I did for concave up functions, if I were to combine these two, we could illustrate another important result. So I'll just erase these dots. Indeed, as we'll be seeing with the second derivative test, if we have a curve looking something like this, then we can see here that the left portion of this curve corresponds to what we saw here, an increasing concave down curve, and the right portion corresponds to what we saw here, a decreasing concave down curve. And what's interesting is that in between the two, we have a maximum point, maximum. And what this shows us is that on either side of a maximum point, the second derivative is negative. And in fact, one of the things we'll soon be learning is that showing that the second derivative, f dash dash of x, is negative at a point will often be used to show that it's a maximum. Okay, we now know what concave up functions are, as well as what concave down functions are. But let me finish by showing you one more thing. Let's say we were given a function whose curve looks something like this. And I'll go ahead and call that y equals to f of x. Well, following what we've just seen, looking at this curve, we can quickly determine where the second derivative is positive and where it's negative. Indeed, as we go from left to right, we can see that the curve is starting by getting steeper and steeper and steeper. In other words, the first derivative is increasing. The second derivative, f dash dash of x, is therefore positive. And we could say that the curve is concave up here. On the other hand, beyond a certain point, roughly here, we can see that it's getting less and less steep. In other words, the gradient and the first derivative is decreasing. In this region, the second derivative, f dash dash of x, is therefore negative. And we could say that the function is concave down. So if I illustrate that further, so I'm saying that this portion of the curve is concave up, and beyond that, this curve is concave down. But somewhere in between, and I'll say right here, there's a point at which the second derivative, f dash dash of x, must equal to 0. Indeed, the only way the second derivative can go from positive to negative is by being equal to 0 at some point. And that point is known as a point of inflection. So I'll just write point of inflection. And I should say that inflection is often written with an X rather than C and T. It all depends on whether you're writing in British or American English. And so a point of inflection is a point at which the second derivative equals to 0 and is a point at which the concavity of the function changes. In this example, the concavity went from concave up to concave down. And we'll be learning more about points of inflection later on in the course. Nonetheless, it is already important to know what a point of inflection is. And there we have it. We now hopefully have a much better understanding of what the concavity of a function tells us, as well as a much better idea of what the sign of the second derivative tells us. And that's it for this tutorial.